All right, here we are on day 4 with parametrics. We're talking about particle motion, and some of this motion you already actually know about. So there's some things you have to know, things you have to memorize. So we know we have a position vector, say f of t, g of t. So if I want the velocity vector, I would take the first derivative of each one of those. Now I didn't write this down, but the acceleration vector, that would be your second derivative. All right, if we want the speed of a particle, all right, speed of a particle is this right here, the square root of dx dt squared plus dy dt squared. All right, we saw something similar to this one on the first day when we talked about vectors and we talked about magnitude. This is kind of the same formula for magnitude as well. Now, total distance traveled is basically the same integral speed, but you're doing the integral of it. All right. And think about it. Speed would be miles per hour. So if I integrate miles per hour, it's going to take me back to miles, which would be my distance. All right. Actually, I did have the acceleration vector here, and there you go. It's the second derivative of each one of those. All right, so let's go through a couple of these examples. I already have them written out, but I'm just going to walk you through each one of them just in case you were confused. All right, so let's look at this first one. And a particle moving along a curve in a position or is at position x of t, y of t at time t for t is greater than or equal to 0, where, and we've got x of t and y of t here. Let's find the velocity and acceleration vector. Well, that should be fairly simple. Your velocity vector, you take the first derivative of each. So you can see that I took the first derivative of each one of these things right here. Don't forget the derivative of a constant is 0. It's been a little while, but you should know that. All right, so I have my velocity vector right here. If I want to find it at t equals 1, all I do is plug in 1 for t. That's it. All right, right here, for my acceleration vector, I found this second derivative. So basically, if I have my first derivative, I have my second derivative, or I can find it. All right, here, now 2 is a constant. That means for everything in my acceleration, the y, it doesn't matter what the t is always going to come out as 2. All right, and here, t equals 1. When I plug it in here, I get -6 plus e as the x component. All right, now the third one, or part B, if I want to find the speed of the particle at time t equals 3, well, we have our formula. Speed, and remember, speed is always positive, which hence this formula will always come out a positive. Square root, this is dx dt, all right, squared plus dy dt squared. And if I want to do it at 3, I'm literally just plugging 3 in for these t values right here. And then I use your calculator. Don't forget, you got to round to at least 3 decimal places. Here I did, you may want to keep more just to be on the safe side. So you're finding, basically, it's the absolute value of v of 3, okay, is really what it is. Okay, part C, find an equation of the tangent line to the path of the particle at time t equals 2. So we did this yesterday, okay? And remember, when you're finding an equation, you have to have dy dx. All right, so dy dx was dy dt over dx dt. Now this is at t equals 2, all right? So here, find the equation. Okay. So here, what I did was I took, and I think this should actually be, well, no, that's the X values. I'm sorry. Okay, so here, you kind of missed this step right here, but you take X prime of 3 and you plug it in. It's -3 times 3 squared plus 4 plus e to the third. Or, I'm sorry, 2. Sorry. So that should say 2. Sorry about that. Okay, and then same thing, y prime of 2 is if I'm taking y prime, which is this right here, and I say 2 times 2, and then I minus 1, I get 3. So this is where I'm getting, so like this comes out to be -8 e squared, but I put it in the denominator because dx dt goes in the denominator, and this comes out to be 3, which is on top. Okay, now, remember the other thing you have to write the equation of a tangent line is you have to have a point. Okay, so you have to go back to the original x and the original y and plug 2 in. So I would go all the way back up to here and I would plug 2 into here and 2 into here, which is what I've done. So you get e to the t2 minus 5 for x and then -5 for y of 2. And then you can see my equation that I've written. Remember, y minus y1, so y minus -5 turns to a plus. We put our slope in, and then x minus. Now, notice here, I put all of this in parentheses because I would eventually have to distribute this negative. You don't necessarily have to, but that 5 would eventually become positive. So be careful about how you put it in needing parentheses and such. All right, moving right along. Let's look at some more examples. So let's look at number 2 right here. A particle moving is at position at time t equals greater than or equal to 0, where, okay, so we've got this right here. Now, this time, instead of giving x and instead of giving y, they gave us these values right here. Okay, so one of the things we need to do is practice putting these things into the calculator as well. Now, let's go. I want to do this in Desmos and see it. Okay, when we're plugging it in, we want to do tan inverse. Okay, so here we go. Remember, inverse tan is underneath functions. We do tan. Okay, and this is e. So you can just put e and then raise to the negative t. Okay, or actually, let's use x. Now, here, and you may actually want to define this. Okay, and I don't know, can you say dx? And this is one thing you'd have to like play around with. You actually don't want to, because it starts to put like a slider. So can we say x prime of t like that equals? Does that work? Not really. All right. Okay, we can just do x of t if you want, actually, not x of t. Just do like f of t like that. All right, and just so that it's defined, okay? Or x, I'm sorry. Keep messing around. Okay, and then same thing, we'll just call the y g of x, okay? So here, the y value is that thing over there. All right, so I'm just gonna type it in, equals, all right, 3x divided by 1 plus 4x cubed. All right, so here we go. Here's the two graphs. I don't know if the graphs are like important here, but putting these things in can help us in the long run. All right, so say if I want to find the speed of the particle at time t equals 1. All right, so we're looking at A here. So basically we want to find v of 1. We'll look at the formula. Okay, we're going to do this right here. And basically you're plugging in 1. Now you can physically plug in each one of those, but watch how I do this on the calculator. All right, make sure this is defined like this. And so now what we can do is we can take the square root. Okay, now we want f of 1. Make sure you have the parentheses squared. Okay, and then I want g of 1 squared like that. And look at our value that we come out with. Again, round to 3 or more decimal places right here. So 0.69589, or on my paper, I put 0.696. All right, right here. So make sure you practice putting things like that into your calculator and can get the value. Easiest way is to define what a function is. Sometimes they define it for us. You cannot put dx dt and dy dt. So just letting you know that. Now I'm going to keep them in there for a little while because I might need it later. Okay, now find the average speed of the particle. Now we've talked about average speed before. Okay, now think about it. If I integrate speed, it goes back to the distance. Okay, but I just want the average of speed. Well, anytime you talk about the average of something, you're dividing it by like the difference of your two numbers. Okay, so that's basically what I'm doing. I'm multiplying by 1 over 4 minus 1, the difference of my bounds right here. Okay, well, what have I done? All right, you can take this right here. All right, Desmos, let me cancel that out. Okay, and it's the integral, and I think we figured out in class we can actually do integral, but here, I want to do this first, 4 minus 1. You can make that a 3 if you want. Integral, if you do INT, there we go. You can do 1 to 4. Okay, now this is absolute value. Remember, speed is absolute value. Okay, actually don't, it's going to come out the absolute value. It's actually square root. Okay, and it's f of x. Okay, close that parentheses and square. Okay, plus, now go do g of x squared, like that. All right, and it should, and oh, here's the reason why it's not coming out as an answer. Make sure you arrow out all the way to the side right there. So use your arrows and then put dx. Okay, you have to put the dx in there to be able to get the decimal. And you can see what the answer is right there, 0.20860. I rounded it to 0.209 on my paper right here. Okay, so pay attention how you put it in. Notice I haven't had to actually keep typing this in because I have it defined already in my calculator. All right, so it does make it a little easier to actually put it into the Desmos calculator. All right, C, find the distance traveled over time from here. Okay, distance traveled. All right, distance travel is basically just taking that same integral and it's the speed. Okay, or you take the speed like formula right here, and you're doing the integral from 1 to 2. So again, practice putting this in. Guys, you can't answer or ask questions. So INT is integral. If you're having trouble typing that in, you are welcome to find the integral underneath functions. You just need to like scroll down. There you go. It's underneath calculus. So there we go. 1 to 2. Okay, it's the square root of, all right. And again, I already have it defined. I don't have to keep retyping out like the inverse tan of e to the negative x, because that can get a little complicated. Just remember when you do integrals, arrow out to the side and put your dx in there. So 0.406, 0.407, however you would like to write it. All right. Now, number 3. A particle moving along a curve. Okay, so notice again, just like in number 2, they gave us dx dt and dy dt. For t is greater than or equal to 0. At time t equals 0, the particle is at position 2, 5. All right, so they're giving us the different derivatives. They're giving us a position when the particle is t equals 1. All right, this is something we have done before. Now, again, we're doing parametrics with it. Okay, so find the slope of the tangent line to the curve at. All right, so the slope is dy dt over dx dt. Well, guess what? They already gave it to us. We already had the two derivatives. Now we just need to divide it and plug in 1. All right, so it's basically sine e to the negative 1 over ln of 2 once I plug that in. Okay, so 0.519. All right, now part B. Find the x coordinate of the position of the particle at time t equals 3. Now, pay attention. They gave us when time t equals 1. So that's where we're going to start with. This is our initial position. Now, we want to find the x coordinate. Well, this x coordinate started at 2. So what we do to find x of 3, we start at the initial, which is 2, plus. Okay, now, what t value did the initial start at? It started at 1, and we're trying to find the value at 3. And you integrate your dx dt right here. Okay, if I plug that all into my calculator, this is the value that I get. So make sure you understand how to write this. And on FRQ, they're going to want you to write that out. So make sure you write that out right there. We don't know how to take the integral of this. Well, actually, I guess we do. We could do integration by parts, but it's not going to be easy. All right. Now, let's look at the last part. And the last one is, we just found the x. Let's go find the y. Okay, coordinate. So again, they gave us, and let me put this underneath here. Okay, t equals 1. Our y position is at 5. So our initial position is at 5 right here. Okay, and that 5 started at t equals 1. And we're trying to find when t equals 3. So you put that at your top bound. All right, we're integrating dy dt right here. Okay, Now, again, that we don't know how to integrate that. So we put the whole thing in our calculator and we get 5.138. So this is essentially recalling some things that we've done before in AB, but now we're doing it on the parametric level. All right. So know how to find the different, the positions at different positions, know how to find slope, know how to write the equation of tangent line, know how to find the distance, travel, know how to find speed, and so forth. All right. If you have any questions, just let your teacher know.